Okay, once more it's time to get started. So, today we are going to continue implementing the PPU registers and memory mapping of the PPU into the bus. So, the last thing we have been working on was creating the registers, and we managed to make the address register and data registers, or somehow some of it. I made the implementation of mirroring with just a copy paste without making an extensive reading of it. So I will now take time to read it and understand it. So before going to connecting the PPU to the bus. So mirroring. One thing that isn't covered is how mirror VRAM address is implemented. Again, the NES Dev Wiki provides excellent coverage of this topic, mirroring. VRAM mirroring is tightly coupled with the way NES implements scrolling of the viewport. We will spend enough time discussing this in one chapter in the chapter about the scroll. For now, we can just code the mirroring behavior. NES uses 1 kilobyte of VRAM to represent a single screen state. Having 2 kilobytes of VRAM on board means that the NES can keep a state of 2 screens. On the PPU memory map, the range 2000 to 3000 FFOO is reserved for name tables. Screen states. So screen state. So name tables are the state of the screen. Okay, so that is what it means. I was wondering that last stream. So it says 4 kilobytes of addressable space. 2 additional screens have to be mapped to existing ones. The way they are mapped depends on the mirroring type specified by a game. NES files have this into the header. Yes, so this is the header that we have been referring. We have been loading when loading the NES ROM file. So here are the 2 kilobytes of virtual RAM from 800 to 400. No, sorry. From 0 to 400 and 400 to 800. With horizontal mirroring, let's make this a little bigger. So the memory 2000 to 2008, I suppose, is the first part of the VRAM, and 2800 onward is the second part, while with vertical mirroring, the first part is the low VRAM, and the second side is the high VRAM. So yes, this is kinda understandable. So basically, if you have horizontal mirroring, that means that the 2 screens are one on top of the other. With vertical mirroring, it means they are side by side. For example, for horizontal mirroring, this one, address spaces 2000 to 2400 and 2400 to 2800 should be mapped to the first 1 kilobyte of RAM. So yes, that means this is repeated. The first and second are repeated from this 800. So So yes, so it is 400 in one screen, 400 in the other screen, and that is the 400 bytes in the first kilobyte. Addresses spaces 200, 2800 to 2300 and 2600 to 3800 should be mapped to the second kilobyte. So yes, so this is the same as this, and this is again repeated the same as this. So this makes very straightforward, I think. One way to codify that is, and this is the code that we copied and re-implemented in GdScript. And now it's time to connect to the bus. So right now the bus takes a ROM in the new function, and it creates a PPU on startup. I am not happy with that implementation, so I agree it should have a PPU reference on the memory, but let's see how it fits in our implementation. So let's see the NES memory, and we have the ROM, and now we can add the PPU. Let's see, how did we initialize the ROM? So when doing reset, we set the ROM to null, but we don't care about resetting the PPU. We can reuse the same one. Where is the ROM assigned? I don't see the ROM being assigned anywhere, is it? ROM equals... No, it's not being assigned yet. Do we have a subclass of this? Or it referred anywhere else? So in here the memory is being set, created. This is the CPU 6502. Doesn't sound like it should use the NES memory, in my opinion. NES ROM unit test. So yes, and it is assigning the ROM directly. Well, yes, we can assign a PPU in this same way, probably. Else, how are you? Going to lurk? Okay, you are welcome to lurk. Yep. I think I am fine with the idea of having the PPU assigned this way for now. So, now that we have a PPU, we can make sure we read it properly. So PPU registers, and it says it is not supported yet, but it is time to support it, I suppose. So let's see how is this implementation working. It is just creating and assigning a new PPU. So it should set the mirroring from the ROM. Okay, that's a good point. So let's do this. We're going to create a setter function, set PPU. and create a function for it. New PPU, and it's going to be an NES PPU. If PPU PPU equals new PPU, if PPU not null, and ROM not null, and let's bring this to a new screen to have a little more space, so we can assign the ROM of this PPU. So we can assign the CH share of the ROM, and we can set the mirroring as well. Okay, so we should probably rename this function to keep the same naming convention. So let's name it screen mirroring instead of mirroring. Let's find more usages. Okay, it's only 2, and replace them. Perfect. So now I want another function for setting the ROM. A set function is going to be equal to set ROM, and set ROM is going to be very similar to set PPU. Hey Cricket, how are you? Are you winning, son? So whenever the ROM or the PPU is changed, it is going... Actually, we could probably move this to another function. Update PPU hope things are going good. Are you referring to my things or your things? So in my side, this is going great. We are having fun starting to work with the PPU. There is a lot of excitement in here. So update PPU yeah, update PPU memories. Okay, I suppose. But so now we can call that function in here instead of repeating the code. This music is so similar to Ninja Turtles. Is it really royalty free? Well, it says it is copyright free. Okay. So it's just inspiration, I suppose. Is it a smelly PPU? I don't know, but for your excitement, I think the first game that we will be able to play is Pac-Man. So you may want to see that. It will be maybe not today, but definitely tomorrow. Feels like I am at an arcade. What do you say that? Because of the music? Anyway, so now that we have done the initialization, we can provide memory mapping for the registers. So now, memory read. We have already done this. So we have a list of memory values that should not be being written ever. So yes, we can make sure that that doesn't happen. So memread. Yes, 2000. So we can say if address in this list, I am converting rows to GdScript. Zero 1 3 5 6. So I could directly make an assertion instead, since this is a panic. So I can assert address is not in this list. With this message, tempted to read, write only address. Tempted to read from write only PPU address, and we need to format this, and I think the way to format this is %04x, and that is because % is for escaping, 0 means complete blank spaces with zeros at the front, 4 is the number of characters we want, and x means it is a hex value. So this goes away, and now we can do the real read of the value. We can return, wait a second, oh, there is a read data function, yes. Specifically for 2007. And what about 2004? Why is it not listened at all? Okay. So I can match the address now. Yeah, actually that will not work. So if address equals 0x2007, good work so far, thank you. And how are you doing in your progress? I want to hear something about the tactic games, because I have not been recently in any stream related to that, so I would love to hear it. So in this case I am going to return on the PPU. Oh, actually I also want to assert that the PPU is not null. In this case. So read data and it takes no argument. Perfect. Yes. So if it is bigger or equal to 2008, we have to make the mirroring work. Let mirror down address, memread mirror down address. Let me understand, what does this mean? Why are we doing a recursion now? Var mirror down address equals this address, which is the same as this apparently. Yes, exactly the same. I'm going to return the mirror down address. So what is this change? I want to understand that. So how is 2008 onward in the bit flags? So a hex 2008. So it means it has the same bytes, but it takes... Okay, so basically it is taking the first page, the memory, with... No, it's not the first page. It is removing this byte. Okay. And what is register mirror end? This. Aha. So it's a big number. Wow. I don't really know how this works. Let's see if we have some explanation here. So from 8000 to FFFF, it returns from program ROM. I think we have that. It's this, yes, we have this, and the else condition is taking care of the rest. So, what is covered and what is not? 2001 and 2. So it is allowing to read 2002 and 2004, despite they are just the second. Oh, it is the data. Okay, so it should be allowed. Okay, sorry about that. 2005 and 6. Seven is being read, but the 2002 and 2004 are not being handled in this code. That is what I am trying to understand. And what is it? Is it read only or is read? Is it write only? OAM address. 2002 is the status. It should be readable. So I think. Wait. Yes, so I think by default it should. Now I am confused. Wait, I think in rows it will fall back to the default. Confused. I am in the right place. Yes, I have done this. Here I am. So, this is a match. We have from RAM to RAM mirror ends. And what is that range? Let me remember. Okay, 0 to 1 FFF. So it does not count. It's not accounted. In this list, it is going to panic. 2007, it will make a read. 2008 to the end of the register, it is going to make the mirror down and read again. And this is the program, and any other case will include the 2002 2004 so this is why actually it is going to ignore memory address. I don't like that a lot. I think reading to the status should be allowed. It's the status and what else? The status and OAM data. I am not very smart with this, so for now I will ignore it. hopefully there will be more explanations later. So what I am going to do is make an assertion. Uncaptured case for memory address, and I want to copy this. This is a little strange. I am under the impression that this should be reading on the PPU THR-ROM, but maybe I am wrong. So let's see how it behaves to writing on the memory now. So RAM makes this its usual work. Writing to 2000 is going to write to control. What did I do wrong? Oh, I want to exit to return a value. Okay. Now it's time to write. I probably want to emit this signal. So the value is going to be this, and I am going to emit an observer, and this is bar, and read date. Perfect. I also want to emit an observer with this value. Because I want to emit it with the right address. Otherwise, this is going to emit it with a mirror down address. Perfect. Now I can continue working with the memory write. So this PPU not supported, this deleted in here, and I am going to remove it now from here. So I want to match address. So in the case of 2000, I'm going to write to control the value. Is this correct? I think it is. In 2006, it writes to address. Yes, and I also want to emit the observer, and the observer, as I see it, is emitted right before the actual change. So the address is the same. The previous value is ppu.control. Wait a second. How is it called? Register control. Okay. Thank you. Register control dot value, and the new value is p value, and it is making a write 8. And in the case of the address, it is register address dot value, new value is p value, and it's a write 8. What I am doing wrong? Argument 2 0, 1, 2, so it should be integer, but this packet byte array, and that is not true. Why does it think it is true? I see. So value is a packet byte array. So I want whatever was the last value set. So old value equals to PPU register address value 0 if PPU register address high pointer is actually I can make it this inside of this. So from the value, this is a pair, 0 if it is high pointer, 1 otherwise, and I don't even know if this is correct or not. Because what would I want to return in this case? The value that is being flipped, or the last value that was set? High pointer is true, set address, blah blah blah, date, high pointer means it is going to set on the high. So that means this should be inverted. So we show the last one that was assigned, which I believe is what we really want. Okay, perfect. I don't know if you understand. I don't know if I understand. 2007, and we choose write to data. PPU write to data and pass p value. And I think I want to emit There was a buffer, internal data buffer, yes. Do I have something that returns the internal data buffer without changing anything? No, there is not. Well, whatever. I don't know if this is going to be correct, but I am going to use it as is. The observers are, for now, for debugging. Eventually they will be important for some optimizations. Okay, and in the case of 2008, to the end of the mirror, it is going to write memory. So it seems like we are using part of the RAM. So if address in range 2008 to the PPU register mirrors ends, is range inclusive? No, it's not inclusive. And is this one inclusive? Yes, it is. +1. For this case, we're going to do this. It's actually this one. And make the memory right. Mirror down address, p value, and I want to assert pass and uncatched case for memory address. Same error message. I need a return in here to avoid Xing this if and going directly to the assert. So this should probably be an assertion. Assert false. We don't want to go to read-only space, to write on read-only space. Okay, so we have done stuff as is. The communication with the rest of the register is similar. I leave this exercise to the reader. So what are the rest of the registers? Which registers did we implement? So we have register address and register control. Let's read again. We have control. What is mask? 2006 and 2007 are address and data, and they are implemented. Read data, write control, write address. So address is write only, data is read only. 3 register controls internal memory OAM that keeps the state of sprites. 2003 OAM. So OAM address and data are exactly the same as 2006 and 2007. So we can have bar register OAM address is an address register .new. And we can do around here. Where is my music? Oh, that was a short list. Do we have another playlist to check? Okay, let's try this one. So here we are going to create a function, write to OAM address value int void register OAM address update value. And we have read data, and now we are going to make read func read OAM data integer. So let's copy this and let's change it to match the OAM data. Register address is register OAM address. Do we increment the VRAM? I think not. Maybe yes. Wait, that would be maybe responded in here. 2003 and 2004 object attribute memory, the responsible for the sprite. Direct memory access 4014 for fast copying of bytes from CPU RAM to OAM. Okay, so the status is read-only, so indeed it should be possible to read it. And do we have a status implemented? Status and control is the same, I assume. Wait, that doesn't sound about right. Yeah. It should not be possible to write to a read-only. This 2002. Which one did call to write control? (2000). Okay. 2000 is controller and 2002 is status. Okay, perfect. Never mind me. So I don't yet know what is the content of the status. So I am assuming that I have to look at here to find everything I want to know. Perfect. So 2001 is color emphasis, PCR, sprite enable, background enable, sprite left column enable, background left column enable, grayscale. Okay, so status has three flags: B blank, sprite 0, hit, sprite overflow. Read resets write file for 2005, 2006. Find scroll position. 2006 PPU read write address, should write most significant bytes, less significant bytes. Yes, so it's the address. OEM read write address. I kind of understand. So we have fully done the controller. I think we can go one at a time and see what we are missing. The PPU has an internal data bus that it uses for communication with the CPU. This bus called the IODB in visual blah blah, and PPU hand latch NES CEX UX. Oh, those acronyms behaves as in an 8-bit dynamic latch to capacitance of very long traces that run to various parts of the PPU, writing any value to any PPU port. even to the nominally read-only PPU status. Will fill this latch. Reading any readable port, PPU status OEM data, PPU data, also fills the latch with the bits read. What is a latch? I need translation, sorry. So that is a very bad. So okay. It is not a good description for me. Reading a nominally write-only register returns the last current value. To do the unused bit of PPU status. This value begins to decay after a frame or so, faster once the PPU has warmed up, and it is likely that the values with altering bit patterns, such as 50, 55 or AA, will decay faster. What? We'll ignore. So controller is a write only. Various flag. This is implemented. Equivalently, bits 1 and 0 are most significant bits of the scrolling coordinates. See name tables and PPU scroll. What? What is this? It was talking of the controller. Why is it suddenly mentioning something totally unrelated? What is this byte? Oh, bits 0 and 1. Okay, base name table address. That is what it means. That is the correlation. So if bit 0 is set, add 2056 to the X scroll position. If Y is set, add 2040 to the Y scroll position. Okay. After power reset, writes to this register are ignored for about 30,000 cycles. If the PPU is currently in vertical blank, the PPU status 2002 the blank flag is still set to 1. Changing the NMI flag in bit 7 of 2002 from 0 to 1 will immediately generate an NMI. This can result in graphical errors, most likely a misplaced scroll, if the NMI routine is executed too late in the blanking period to finish on time. To avoid this problem, it is prudent to read 2002 immediately before writing to 2000 to clear the B blank flag. For more explanation of sprite size, see sprite size. Okay, master slave, this condition. Okay, I will for now just ignore the control flags because they are already sorry, they are already implemented. So now is the must. It is a right flag. This register controls the rendering of sprites and backgrounds as well as color effects. Okay. So let's create the same way we make the control register. Let's make a must register. Let's copy this. Comment it same way. Oh, I don't like that. Oh. Now we can name each of the flags. This is how it's created. Let's just copy one. And this is grayscale. This colored G. Second one is how to describe it? Margin left. Hit 1 and 2 enable rendering of the background and sprites on the leftmost 8 pixel columns. Setting these bits to 0 will mask those columns, which is often useful in horizontal scrolling situations where you want partial sprites or tiles to scroll from the left. Okay, so one is margin for the background and the other is margin for the sprite. Left margin background. Left margin sprite. So background. I assume show background is it's the 4. 3 and 4 are enable the rendering of background and sprites respectively. So it's basically fully render or not render. It's a toggle. So sprites. button, the one for sprites is named S. This is 0, 1, 2, 3, 4. Yeah, I did not align this. Maybe I should, maybe I don't. I like how it looks when it is aligned. This is meant to be a string name. Emphasize red, green and blue. Create an RGB red, green, blue. Four, 5, 6, 7. Okay. These are the bytes. Effector of bit 3 or 4, which are the show background and show sprites, is enabled at any time outside of the blank interval. PPU will be making continual use of the PPU address and data bus to fetch tiles to render, as well as internally fetching sprite data from OAN. If you wish to make changes to PPU memory outside of blank, you must set both of those bits to 0 to disable rendering and prevent conflict. Ah, I see. So that's why that's how you redraw an entire screen. Disabling rendering during both bits 3 and 4 during a visible part of the frame can be problematic if it can cause corruption of the sprite state, which will display incorrect sprite data on the next frame. What is errata? This page describes aspects of the NES hardware that may be considered an error in the implementation. Okay. Sprite 0 hit does not trigger at X 255. Oh, I see. Sprite overflow is unreliable due to errors in its implementation. Internal copy to secondary OAN causes a diagonal fetch pattern, causing both false positives and false negatives in the sprite overflow bit. Workaround make sure the NIF sprite immediately follows the A and use the sprite overflow only to time the top of the screen, not the bottom. Okay, I will not see this yet because it's too early for it. It is however perfectly fine to mask sprites but leave the background on. Set bit 3. Clear bit 4 at any time in the frame. Aha! Sprite 0 hit does not trigger at any area where the background or sprites are hidden. Okay. Color control. Bit 0 controls a grayscale mode, which causes the palette to use only colors from gray column 0, 1, 2, 3. This is implemented in a bitwise add with 30. On any value read from CPU in this range, both on the display and through CPU data. So okay, that's interesting. Writes through to the palette through CPU data are not affected. Also note that black colors like OF will be replaced by non-black gray 00. Bits 5, 6 and seller, control emphasis or tint effect, see color emphasis detail. Okay, so basically these are flags and we should have a function to set it like we have for the control. So we have write to control, write to mask, and this is register mask, and we have to create the register mask. Control is the first one, actually. Second is mask. Mask. Okay. It's right only. Render control, color control, perfect. So the next one, 2002, is the status. So this one, so we need an update function just for setting the value. It's a little useless, but we're making use of it here. So now that we have write to mask, let's expose it to the memory. Memory write. The mask is the byte. Let's see, 2001. This is going to be register mask. And we are going to write to mask. So we have write access. 2000 and 2001 are blocked for read, correct? 2003 is read write access. So it has read access according to this. Okay, never mind, let's go to 2002 first. 2002 is read only. Oh, so that is why it was not listed. It was part of the quote exercise. So could it be a match, I suppose? Match address. This is case 2007. We have already removed these cases, so we can make them a case. Make an after pause. Pattern 0, 0, 1. Now let's go OX 2002. First pause to do. So the idea is to cover every possible value. And continue accepted. Now it's not anymore. Okay, I will just copy and paste it. 0, 1, 2, 3, 4, 5, 6, 7, 2008. Okay, so this is out of this range. So let's see that later. Entonces this is the else condition. Is this valid syntax now? No, it is not implemented. It is not implemented yet. So I am just making an extra case and make an assertion. Unexpected memory address. So this will never happen because of the default. Now 4040. This cannot happen with this condition. So we have RAM range, PPU register, ROM memory. ROM memory goes from 8000 onwards. So I don't know why is this particular address part of the PPU. I mean, it is listed in here, 4040. This is direct memory address. It should be from this point onwards. So question is, why only that byte in particular and not the rest? Okay, perfect. So music stop it again. Oh no, I just muted it for myself. So it says not everything returns a value. Which one doesn't? Oh, this one. Okay, done. So we have control, we have mask. Next is the status. PPU status register access is read-only. This register reflects the state of various functions inside the PPU. It is often used for determining timing. To determine when the PPU has reached a given pixel of the screen, put an opaque non-transient pixel of the sprite 0 there. Do not read this address to wait for exactly one vertical redraw. On NTSC, it will sometimes give false negatives, and on Dendy, on some reboots, will always give false negatives. Additionally, on PlayChoice 10, the Seed AP supervisor will reject the game if the game leaves NMIs disabled for too long. Instead, use NMI for timing. Okay. Aha, so we have a lot of bytes. PPU open bus returns stale PPU bus content. I am not sure what that means. So sprite overflows, the intent was for this flag to be set whenever more than 8 sprites appears on a scanline, but a hardware bug causes the actual behavior to be more complicated and generate false positive as well as false negative. TPPU sprite evaluation. This flag is set during sprite evaluation and cleared at dot 1. The second dot, I suppose, is the second pixel of the line. Of the pre-render line, yes. Sprite 0 hit. Set when a non-zero pixel of sprite 0 overlaps a non-zero background pixel. Cleared at dot 1 of the pre-render line. Used for raster timing. Vertical blank has started. 0 not in B blank, 1 in B blank. Set at dot 1 of line 241. The line after the post-render line. Cleared after reading 2002 at dot 1 of the pre-render line. I don't know what dot means this, but let's give it a shot. Let's have a class for it. As we have for the rest. So this is going to be the status register. So we are going to create these 3 flags. No, actually it's the last ones. 5, 6, and 7. And they are O, S, and B. This is in B blank. This is sprite 0 hit. And this one is sprite overflow. Okay. And this is read only, so no need no need for write access. So in the memory on write it should fail. It is 2003, right? No, 2002. Let's make an assertion. Attempted to write to read only PPU address and then the address. Perfect. 0, 1, 2. In this case, for 2002, we are going to emit the observer. Val is going to be register status. Yeah, I never created it. My bad. Yeah, let's name it like that. Perfect. Stat dot value. We're going to emit and return value. Okay, 2003 is right only according to this, and is not implemented. So it's right only, so it's listed in here. Perfect. I don't see it in here, so we have to create it. OX 2003. We want to emit it, and this is the OEM address, so it's register OEM address with value and p-value, and let's call CPU write to OEM address p-value. Perfect, that's it. I did something wrong again. Yeah, so it's like this one. Perfect. Oh, right, this is old value. Perfect. 2003 is right and is not read. Perfect. It's done. Next is 2004. Not implemented. Write the address of OEM you want to access here. Most games just write 00 here and then use OEM DMA. DMA is implemented in the 2A03 chip and works by repeatedly writing to OEM data. Values during rendering. OEM address is set to 0 during each tick. Each of tick 257 to 320. The sprite time loading interval of the pre-render and visible styling. This also means that at the end of the normal complete rendered frame, OEM address will always have returned to 0. If rendering is enabled mid-skyline, There are further consequences of an OAM address that was not set to 0 before OAM sprite evaluation begins at tick 65. This is talking in terms that I don't understand. The value of OAM address at this tick determines the starting address for sprite evaluation for this skyline, which can cause the sprite at OAM address to be treated as if it was sprite 0, both for sprite 0 hit and priority. If OAM address is unaligned and does not point to the Y position, first byte, of an OAM entry, then whatever it points to, tile index attribute or X coordinate, will be reinterpreted as a Y position, and the following bytes will be similarly reinterpreted. No more sprites will be found once the end of OAM is reached, effectively hiding any sprites before starting OAM address. Hey, this is just notes about status and everything. I don't need them for now. What is this song? It sounds very similar to Stranger Things. Still says it's royalty free. So 2004 is read-write OAM data. OAM data port. Access read-write. Read OAM data here, writes will increment OAM address after the write. Reads do not. Okay. So we have 2040s, right to OAM address, write PPU address, This is increment OAM address. Yeah, but increment happens on write, not on read. Let's delete this for now. 2004. 2004 is yet to be implemented in here, and is yet to be implemented in here. So X 2004 and 2007 was also read-write. How is 2007 treated? Okay, so it's write to data. That is the function I wanted to see. 2004 is going to be write to OAM data. P value. And I am assuming we are going to also need an internal OAM data buffer. Just assuming for making this emit. Because OAM data also uses 2 bytes. So where is write to data? Oh, it was never implemented. Was it implemented in here? No, it was never implemented. Interesting. So, following the order, this was 2000, 2001, 2002, is that correct? Yes, status is 2002. 2003 is OAM address. So we have read data and read OAM data, I assume. 2005 was the scroll. Two 2006 is the address. 2007 read data. So this is read write OAM data, and this is also read write. So we can make this a variable, PPU data of type integer set is going to be write data, or was it write PPU data? Write to data is not anywhere else. Okay, so it's write to data, still unexisting. And get is going to be real data. That one should exist. Yes, here it is. And func write to data. So what is meant to be write to data? And write to OAM data. This is not TP for now. Oops. What I am missing? A comma? I don't think so. Oh, I was. Okay. So set is write data, get is read data returns an integer. And we want func read OAM data returns an integer, and it is going to be similar to this one. Now we will have increment. Okay, read does not increment. I have to remember that. CHROM OAM data. Here we go. So we want register OAM address. Oh, So this is an 8-bit address. Maybe. Let's read this. OEM address. I see. So I made a wrong assumption. Of the address register of the OEM address register. So this is just an integer. Register 8 bits. This was the name. It kind of is, but at the same time it is not. I think we can use just an integer for this one. That is going to be write to OEM address. And read is address is read also. Yes, it's read right. Okay. So it was 2003. 2003. For read. is not allowed. So that explains why we didn't have this. So the renderer will have to do it, I assume, in this same class. So increment OAM address. So the increment happens on write, not on read. So I can simply return where is the increment? Func increment OAM address void OAM address plus equal 1, I assume. Write the address of OAM you want here, Moscane, blah blah blah. Where did I read that it was? Increase it only on read. Write OAM data here. Writes will increment after the write. Reads do not. Okay, so yes. Writing to the OAM will increment after, but reading OAM doesn't. Perfect. So writing OAM data means OAM data to register OAM address equals value, and then increments by 1. Perfect. And it is 2004. So bar OAM data so it is repeating OAM data. I will just keep it commented. It's right to OEM data. Get OEM data. Maybe I can make this one. No, I don't want. Maybe I can rename it OEM buffer. Or object attribute memory. Let's search. Now we can uncomment this. Right, missing bar here. Now what? Oh, cannot use resize. Or check attribute memory. Get OEM data not found. Read address, write address, read OEM data not found. What do you mean it's right here? Oh, it's read, not get. Okay. Perfect. So now the memory 2004 bar equals CPU OEM data going to meter server and return value. That is read. Now we have to do write. Okay. The old value is going to be OEM data, and it is supposed to not increment on read. Perfect. Old value, p value. Did I? Yes, I closed the script. So this is the new set now. Perfect. Oh, write to data is unimplemented yet, but I have not get there. So next is scroll 2005. Common name is PPU scroll. Description PPU scrolling position register. Write access, write twice. Oh, so you write one for X and one for Y. For Y. The register is used to change the scroll position, that is, the PPU which pixel of the name table selected through PPU control should be at top left corner of the rendered screen. Typically, this register is written during vertical blanking. So that the next frame starts rendering from the desired location, but it can be also modified during the rendering in order to split the screen. Changes made to vertical scroll during rendering will only take effect on the next frame. After reading PPU status to reset the address latch, write the horizontal and vertical scroll offset here just before turning on the screen. Read PPU status, possibly other code goes here, LDA can position X, store PPU scroll, LDI can position Y, PPU scroll. So it's a right, and it flips one and the other position. So it's right only, cannot read. So let's make sure it is not allowed. In 2005, and it is blacklisted. Okay, perfect. So we are going to need bar scroll packet byte array equals 0 0, and this is going to be the scrolling, and we are going to reset it on init. Do we have a reset? I think not. We don't have a reset function. Okay, awesome. So we are going to have a function write to scroll. Actually, we will probably need a register, but I want to avoid doing that. Try to mask. What is it doing down here? Should be right after control. And write to OAM, read OAM address, write to OAM data, read OAM data. Function write to scroll value integer actually let's name it a register better. Register scroll, and it's going to be a packet array. Now let's name it scroll offset. Okay. Really, this doesn't need any. It already has that default value. If next scroll is X, scroll offset could also be a vector2 integer. Scroll offset y equals value next scroll is x equals not next scroll is x, and this returns void. Okay, this is write only. It should write twice. Reset. Which pixel is in the name table? Typically, this is written in B blank, but it can be changed. Changes make vertical scroll during rendering. After reading CPU status to reset the address flag, write on the horizontal and vertical scroll offset here shows turning on the screen. Horizontal offset changes from 0 to 255. Normal vertical offset changes from 0 to 139, while values for are treated as -6 through -1 in a way, but the tail data is incorrectly fetched from the attribute table. By changing the values here across several frames and writing tiles to newly revealed areas of main tables, one can archive the effect of a camera panning over a large background. Okay. So, what I want to make sure is that, and I had some assertion here, yes. I want an expected 8-bit number assertion. Perfect. Common name PPU address. Register PPU address. Access write twice. So we have address implemented properly. So I want to have bar register scroll type integer set equals write to scroll get equals write only from bus. So it's in theory not allowed. It will return 0 no matter what you do. So from memory we cannot read it and we want to write it. So it is 2005. PPU old scroll equals PPU scroll offset vector 2 integer. Let's find another playlist. Bar old value equals old scroll.text if PPU dot if not off next scroll is x. So that would be y if next scroll is x, else old scroll x. Because if the next we are going to write is x, that means the last we have written is y. How is it going? Doing fine. So we have we have been left with a lot of homework at the end of this chapter. So I am looking at the specification of each register into the wiki documentation and implementing one after the other. So these are memory addresses. Roland could know more about each of them. But yep. Equals p value. I want to emit the observer with the old value and p value. Oh, this is PPU. Register scroll. Perfect. So how are you going else? So address 2006 is implemented. It should be write only, correct? It's write only and it's implemented. 2007 is read write. So we have boost conflict during raster effect. If second write to PPU address happens as data 2007 is read write. PRAM read write data register after access. The video memory address will increment by an amount of determined by bit 2 of what? Let's see. I am doing well. I am in super crunch mode for my RPG project. They asked me to do some splash art for the kiosk at the convention. I am trying really hard on it, so maybe they will just let me do the art at for the whole thing. So when is the event? When is the convention? Run read write data register after access. Aha! Now I get it. Yes. Yes. Write is implemented and it indeed take no, it's not. Read data increment VRAM. Oh, so it will happen on both cases. Bum, bum, bum. So copy. So it should never be this range address. Assert false cannot write to read only address. And it was 04x address. Otherwise, if it is the RAM value, no return. Palette table equal value. For X, no return. Okay, this should be it. So yeah, I am getting the address, incrementing the address, and setting it depending on the range. From 0 to 1FF, it is the ROM, it cannot be written. From 2000 to 2000FFF, it will update it. From 3000 to 3003FF, 3EFF, it is not expected to be used, I don't know why. From 3F00 to 3FFF, it is the palette table. And any other case, it is unexpected. Perfect. So I finally implemented write data. So I can use view data equals the value. And read view data. Need to be named register view data. Well, who cares? Actually, that makes sense. Wait a second. Oh yes, we cannot do this. Oh, we can. OEM data will not auto increment on read. Okay, only on write. That's fine. Now that we rename it that as register, we can rename this one again to OEM data. What part are you working on? I am working on the PPU. So right now we are on the chapter 6, starting with the PPU. When I am done with these first 3 parts, with this the chapter 6, once I am done with the chapter 6, I should be able to have Pac-Man rendering without scrolling or anything. I am currently working on the PPU registers. The registers are just some hard-coded memory directions that are used to control the renderer. So you have these memory addresses, the controller, the mask, the status, and some more stuff that are used to change the rendering. In example, the scroll is the position of the screen, the one that you see the changing when Roland is programming, and it is a single memory where you write twice. The first time you write, you are setting the X position. The second time you write, you are setting the Y position, and so on and so forth. Address and data are like position and value. So you set the position you want to read and read or write the value of that position. OAM are the sprites information. The sprite. OAM, object attribute memory, are the sprites, and the normal ones, address and data, are the background address and data. So they have more, they are bigger or smaller depending on that. Of course, the address is much. The background is takes much more memory because it is not. There is not. You cannot have too many sprites or too many objects in the screen, and they don't have that much information. They have like the sprite tile ID and the X position and Y position and some more stuff that I have yet not seen. Yep. This is the entire memory of the PPU. This from 0 to 2000 is the CHR ROM, the one that you sent to Roland, that you have explained it many times. 2000 to 3FF are the name tables, that is the actual screen, so the background. So this is the tile set, and this is the tile map as we used to name them in Godot. 3F to 00 to 4000 are the palette, so those are what are the colors for each of the palette. Yes, the name tables are the actual tiles that are on the screen, and there are 2 screens in the memory. So 2000 to 2800 is one of the screen, and 2800 to 3000F or something like that is the other screen. And depending on the mirroring, it will be mirrored vertical or horizontal, like this. This is horizontal mirroring, this is vertical mirroring. It is called mirroring, but it is actually repeated, not mirrored. But is not that kind of mirror. Anyway, so I wanted to at least finish these registers before ending the stream, but it is getting a little late. It is a misleading term, but when you are working with Yeah, I think the written would be shadowed memory, but it is not really shadowed. I don't know why they called it mirroring, honestly. So, what was I doing? Yes, I was in here. So I am in 2007. This is implemented. So the last one, the only one that is missing is OAMDMA high address. So this is the only one that is missing. Common name PPU data, description PPU data port, read write, VRAM read write data register. After access, the video memory address will increment by an amount determined by the bit 2 of 2000. Yes, this is what I oh wait, I am reading the wrong link. So this is the one. So this is read only. So write only. And OEM DMA register high byte. This port is located on the CPU. Writing XX will upload this many bytes of data from CPU page to the internal PPU OEM. The page is typically located in internal RAM, commonly this value, but cartridge RAM or ROM can be used as well. The CPU is suspended during the transfer, which will take 500 to or 540 cycles after the write tick. One wait state cycle while waiting for writes to complete, plus one on a put cycle, then 256 alternating get put cycle. See DMA for more information. The OAM DMA is the only effective method for initializing all the 256 bytes of OAM because of the decay of OAM's dynamic RAM when rendering is disabled. The initialization should take place within the blank writes through OAM data, generally too slow for this task. The DMA transfer will begin at the current OEM write address. So it is a high byte. I see. I understand. So this is kind of a command. I can mock it. So read is disabled and write. Read data. Wait, memory. It's reading memory. Read memory for. So read is not allowed. Let's see. Yes, there is an assert. It's not expected to be written. Perfect. And on write, this is out of range, so we cannot put it in here. elif address equals 0x440. Was it? Yes. So we are going to emit a signal. The old value is going to be 0. We don't care. The address is this one. The value is p value. Let's hide this. Have a little more clear. PPU. How is this called? OAM DMA. Direct memory access. I don't like that name. Copy RAM to OAM. P value. So now we have to implement this. Func. So let's call it mem copy. And this is going to be called p high byte. Let's assert it an 8-bit value. It's the void. Bar from type integer going to be equal to the high byte shifted 8 bits. Part 2 type integer is going to be the high byte shifted 8 plus OXFF. And for address in range from 2x, so 2 plus 1 I suppose. Actually, this can be I on range OX100, which is from 0 to FF. So we can say RAM address equals right, the PPU has no access to the RAM right now. So I can probably just pass the packet byte array. and assert it is a size got a lurk again. Okay. For byte in DRAM slice OEM data equals we cannot do that. For I in range DRAM slice dot size, yes, this should be 100. RAM address Y, is OEM data sub I equals DRAM slice I. Perfect. Wonder. I wonder how should this affect the... No, it doesn't exist. It should... Does it say it resets the OEM address? The DMA transfer will begin at current OEM write address. It is common practice to initialize it 0 with a write of before the DMA transfer. Different starting address can be used for a simple OEM cycling technique to alleviate sprite priority conflict by flickering. If using this technique after the OEM address should be set 0 before the end of the blank to prevent potential OEM corruption. However, due to OEM address writes also having a corruption effect, this technique is not recommended. Okay, so it is not being written to I, it is being written to register OEM address. Why it doesn't autocomplete? Okay, so when incrementing, if register OEM address bigger than 0x0015, register OEM address equals 0. Perfect. We're only incrementing by 1. So this we are going to call increment in here, and now we can actually iterate the byte. Perfect. So this will do what we want to do. Now we want to obtain the slice bar from int equals key value 58 bar 2 int equals key value shifted 8 or ff bar sliced equal slice from let's name it begin and end to keep the same naming. Perfect. And we pass sliced perfect. This doesn't work. Mm. Ba-bam, ba-ba-bam. Okay, what else? What do we have in memory? The platform. I want to remind, did we have okay, CPU, RAM, IO register, expansion ROM, that is 4020 onward, save RAM, program ROM. So IO register. Can I look at this? So yeah, more or less. So we don't know those the rest of these two. I don't know. This doesn't specify. Oh, so 2A03 is the name of the chip. Okay. So it doesn't say if the CPU can access directly. No, it should not be able to access directly, otherwise why it exists the register. Okay. But I wanted to check the CHR ROM, not the RAM, not the name tables. So I simply don't know. Actually, I can check it on read data. Memory. RAM is going to take it from memory. CPU registers. So do we have direct access to CHR? I see not. We don't have direct access to it. Well, I also did not expect to copy a slice of memory directly from there. Perfect. So I think this is all. I think we are done with the register chapter. We do not have a full test for this yet, but we can at least run and confirm that we are still not failing. Okay, identifier not found bit flag. That is because this is inside the CPU flag. Where else? These three CPU and these 8 CPU. So same as before. And this is the ALU I assume this is scrolling, and this is cycles. Oh, interestingly, we should be able to update this with the scrolling now, in theory, but I would see that later, because I implemented the scrolling, but yeah, we implemented the register, so we should be able to test them. Anyway, we are done with this. Implemented the PPU registers and memory mapping. So yes, we added the PPU. We implemented reading and saving and writing. And implemented set of the ROM and PPU. We don't want this to be posted. It's the status, and we have a new file. Add-ons, Retro Console Emulator, NES, NES PPU.gd. Git commit, implement PPU registers and memory mapping, and boost memory mapping. Git push origin main. Okay, everything is up to date now. So thank you very much for watching. It has been very entertaining this week, and see you next time.